Welcome to Data Do Library. In this video, we're going to review polynomial and rational functions. Let's begin. In this first question, we have to match the quadratic function to its graph. Quadratic function we were given is x squared minus 4. Notice the negative 4 is on the outside, which means it's going to move it down from its original position. The only graph that matches that is obviously this one. In this question, we have other transformations happening. One on the outside, which again would move it down, and one on the inside, which would move it in the opposite direction of what you would think. Since it's on the inside, it's going to move either left or right, and since it goes opposite of what you would think, positive is going to move it left. So the vertex of this function moves down 4 and left 3 units, which again leads us to this answer. Finally, we come to an example that has 4 different transformations. One on the outside, plus 2, is going to move it up. One on the inside of the function, which goes opposite of what you would think. In other words, it goes to the right. We have the 1/2 on the outside, which means this function is going to either shrink or expand. And the rule is that the higher the number, the more it shrinks. The closer the number is to 0, the wider it gets. So this is going to make it wider than your standard mother function. And then the negative flips it over the x-axis. So if we were to graph this, first let's take a look at what the original parabola would look like. This is an x squared function, therefore it's parabola. That parabola's vertex and every point on that function is going to be moved up 2 units and to the right 3 units, which means we know the vertex is now going to be here. This function will also be flipped over the x-axis, and it's going to be wider than the original. So if I'm just sketching this, I'm going to sketch a wider function that's flipped over the x-axis. In this question, we are first asked to write this quadratic function in a standard form. To write it in the standard form, I'm going to use completing the square method. So I'm going to take x squared minus 4x and move the 1 over to the other side by subtracting 1. Now I have to fill this number in. I'm going to take b over 2 and square it and add it to both sides. B is the number that's in front of x. In other words, 4. 4 over 2 squared is obviously 4. So plus 4, and I'm going to do the same thing to the other side of this equation, because whatever I do to the left, I have to do to the right. I'm going to erase this. Now I'm going to factor this, giving me x minus 2 and x minus 2 equals 3 on the right side. So on the left side, I have x minus 2 squared equals 3. If I bring that 3 over to the other side, I now have the standard form of this function, f of x. Now, let's talk about the transformations occurring here. I have negative 3 on the outside, which would make it go down. And I have negative 2 on the inside, which makes it go right. The only graph that matches this is this one. The vertex of this function is here, and that is positive 2, comma negative 3. My axis of symmetry is just the x-coordinate of that, In other words, what is the vertical line that cuts this function exactly in half? X is equal to 2. And finally, to find the x-intercept, I can solve this equation for x. So x minus 2 squared equals 3. I'm going to take square root on both sides. Remember, when taking a square root of a square, you have to put plus or minus on the right side. That plus or minus square root of 3, and then add 2 to both sides. I have x is equal to 2 plus or minus square root of 3 as my two roots. So the smaller value will be 2 minus square root of 3, and the larger value will be 2 plus square root of 3. This question is very similar to the previous one, which we're going to complete the square. X squared minus 10x is equal to negative 28. I'm going to take half of 10 and square it, which would give me 25. I'm going to add 25 to both sides. Now when I factor, I have x minus 5 and x minus 5 as my factors, and that is equal to negative 3, which gives me x minus 5 squared plus 3 as my function f of x. Again, the two transformations that occur here are up and to the right, which gives me this graph. Notice the vertex of this function occurs at 5, 3. Axis of symmetry is just the x-coordinate of that vertex, which is 5. And x-intercept does not exist because it does not pass through the x-axis. In this question, we need some knowledge of polynomial functions and how they behave. Notice that the highest power is even. The end behaviors of this function are going to behave just like a quadratic would. So a quadratic function either goes up on both sides or goes down on both sides. Since there is a negative in front of this polynomial, we're going to have a behavior of a negative quadratic. Therefore, this can be eliminated as well as this one because neither of them behave this way. Since the degree of this function is 4, it means that we will have one less turning point than its degree. So since the degree is 4, it's going to have 3 turning points. Notice one turning point, second turning point, and third in this function, whereas this one only has one turning point. Therefore, our answer has to be here. This is another question that asks to describe behavior at the left and the right hand side as x approaches infinity. Notice again that this is a cubic function. And as we know from parent functions, a cubic function behaves either like this when it's positive or like this when it's negative. In this case, we have a negative cubic function, which means it has to behave like this. So as x approaches negative infinity, it's going up. And as x approaches positive infinity, it's going down. So the graph rises to the right, that is not correct. Graph falls to the right, that is correct. Graph rises to the left, that is also correct. And graph falls to the left, that is not correct. In this question, you're asked to use long division to divide the two polynomials. The first thing we have to do is take the first number, x, and divide 3x squared by that number. 3x squared divided by x is just 3x. Now the reason why we do that is because when we multiply, we're going to put it here, and then when we subtract, we want that first term to go away. 3 times negative 8 is negative 24x. Now I'm going to subtract this whole entire function, In other words, I'm going to change the sign of everything that's inside. So instead of writing negative here, I'm going to change the signs of what's inside. This cancels, and here we have 7x. Now we repeat the same process. 7x divided by x is just 7. 7 times x is 7x. We're going to bring the negative 56 down. 7 times negative 8 is negative 56. Again, I'm going to subtract. In other words, I'm going to change the signs. And notice everything cancels out to 0, which means that these two polynomials divided by each other produce the answer of 3x plus 7. One easy way to check your answer is using synthetic division, which we will do in the next example. Synthetic division very often is a much quicker way to divide two polynomials. First thing you have to do is list all the coefficients. 4, negative 36, positive 36, and negative 32. Making sure that all of the coefficients are accounted for. I'm going to divide them by 8 because x minus 8 equals 0. You add 8 to both sides, x is equal to 8. Bring down the first number. 4 times 8 is 32. I'm going to add 32, giving me negative 4. Multiplying the negative 4 times 8 produces negative 32. 36 minus 32 is 4. 4 times 8 again is 32. And when you add those, you get 0, which produces a depressed polynomial of 1 degree less than what you started. We have 4x squared minus 4x plus 4 as my depressed polynomial. And obviously that is times x minus 8 will give me what I started with. Now we'll switch gears a little bit and we will talk about complex numbers and imaginary numbers. The first thing we have to remember is that a square root of a negative number is going to produce an I, or an imaginary number. So 7 plus, before I even do the square root of a negative number is going to give me I, and then square root of 16. We know that square root of 16 is just 4, so we have 7 plus 4i. Just as in previous example, I'm going to hold off with solving the square root of the number and just take care of the I first. So the square root of a negative number just produces an I on the outside of the square root number. So I square root of 27 is the first step I would suggest. Then you can break down 27 into 9 times 3 because 9 times 3 is 27. Now notice that square root of 9 is just plain old 3, which means I have 3i, and then I still have the square root of 3 left over. Some people like to break it down a little further, making it I square root of 9 times square root of 3, and again, square root of 9 is 3. One thing to remember with imaginary numbers is that they behave very similar to variables. So in this case, I'm going to distribute the negative, giving me 2 plus 3i minus 7 minus 18i. And now I'm going to combine like terms the way I would if these were regular variables. So 2 minus 7 is going to give me negative 5, and 3 minus 18 gives me negative 15i. Now we're going to use FOIL and distribute these two parentheses. One piece of information that you need here is that I squared is equal to negative 1, and you'll see how that comes in play in 1 minute. So when I FOIL, I'm going to do first, which is 9, outer, which is negative 8i, inner, plus 9i, and last, which is negative 8i squared. So as before, I'm going to combine like terms here, which is 9 plus I minus 8I squared. And now, knowing that I squared is -1, I'm going to replace this I squared with -1, giving me 9 plus I minus 8 times -1. Two negatives obviously make it positive. And again, I'm going to combine like terms here, which is 17 plus I. One last similar example. Very common mistake here is that people want to square the 4 and square the 8I and be done with it. That is an extremely common mistake. Please don't do it. Write it out as 4 plus 8I times itself. And then proceed to FOIL. So 4 times 4 is 16 plus 32I plus 32I again plus 64I squared. As in previous example, we're going to replace I squared with -1, giving us 16, 32, and 32I is just 64I minus 64. I'm going to combine like terms, giving me 48 plus 64I. To write the quotient in a standard form, we need to get rid of what's in the denominator. We need to get rid of that I in the denominator. The only way to do that is multiply by a conjugate. A conjugate is nothing more than exactly the same thing you have in the denominator, but with the opposite sign. So I'm going to multiply this by 8 plus 9I. Now I can't just multiply the bottom by 8 plus 9I. I have to do the same thing to the top. So I'm going to do that to the top as well. So now I'm going to distribute the 4 through this parenthesis, which would give me 4 times 8, which is 32, plus 36I at the top. Now the bottom is a little more challenging. We have to FOIL. 8 times 8 is 64. 8 times 9 is 72. I. 9 times 8 is negative 72I. That is how you're going to get rid of those I terms. And then 9 times 9 is negative 81I squared. So just like before, the top doesn't change. 32 plus 36I. Now at the bottom, we have 72 and negative 72I, that cancels. And that leaves us with 64 minus 81, but I squared is -1, so I'm going to replace that with -1, leaving us with 32 plus 36I over 64 plus 81, which simplifies to 32 plus 36I divided by 145. Another way you could write this is 32 over 145 plus 36 over 145I. We'll now circle back a little bit to talking about polynomials. One thing to remember about polynomials is that the most roots you can have is determined by what is the degree of the function. In other words, what is the highest power of the function. So the question, determine the number of zeros of the polynomial function. Simply, at most, it has 3 because the degree of this function is 3. In this example, we're going to use the rational zero test to figure out what are the possible real roots for this example. Notice the graph is also provided to see if our list matches what's on the graph. So in a rational zero test, we need P and we need a Q. P is factors of the constant term, in this case will be 81, and Q is factors of the leading coefficient, which in this case would be 1. So to list all the factors of 81, we just have to think of all the numbers that 81 is divisible by. Always start with the easiest one, which is 1. Next factor would be 3, 9, 27, and last, plus or minus 81. Factors of q, since it's just 1, is just plus or minus 1. I'm going to divide each one of these factors of p by factors of q and get the list of all possible rational zeros, which are plus or minus 1, 3, 9, 27, and 81. Now let's inspect our graph. Notice the first root looks like it's a -3. That is one of the possible roots. The other root looks like it's at a 3, which again is one of our possibilities. And the last one is a +9, which again is on the list. In this example, we don't only have to list all the rational zeros, we also have to test them. So the first thing we're going to do is divide p by q. And again, p is my factors of the constant term, which is 6, which will give me plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And q is the leading coefficient, which is just plus or minus 1, which means my possibilities are plus or minus 1, 2, 3, and 6. And now we're going to start testing them. I would strongly suggest using the synthetic division for this part of the problem. So to use synthetic division, I'm going to list all of the coefficients. But one thing to notice is that x squared is missing, which means we have to put a 0 in for that missing power of x. So we have 1, we have 0, we have -7, we have -6. And now I'm going to start testing those 8 numbers and see which one works. I'm going to start with +1. I'm going to bring down 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1 again. That is -6 times 1 is -6. Notice we get -12 as a remainder, which means 1 is not one of the roots. Next root on our list will be -1. I'm going to try -1. And bring 1 down. 1 times -1 is -1. -1 times -1, +1. -6 times -1 is +6. And we get 0 as the final answer. In other words, there is no remainder, which means we just found our first root. And keep in mind that at most, there are 3 roots in this problem, because that is the degree of the function. So I know that one of my roots is x equals -1. Once I found one of the roots, I can go ahead and write a depressed polynomial based on this new function. So I have x squared minus x minus 6. To find the remaining roots, you now have a couple options. If this is factorable, definitely try to factor and find the rest of the roots. If you don't feel like it's factorable, you can use quadratic formula, completing the square, or just continue plugging the numbers in and see if any of them work. I can see that this is factorable, which means I'm going to put x and x, plus or minus factors of 6 that will make a -1 is 3 and 2, which means this is -3 and +2. So my remaining roots are x equals -2 and x equals 3. So now I found all the roots for this problem. Last topic we're going to talk about is rational functions. In this example, you have to find a vertical and a horizontal asymptote. A vertical asymptote is easily found by setting the denominator equal to 0 and solving for x. So if I subtract 4, I have -x equals -4, x equals 4. That is my vertical asymptote. To find a horizontal asymptote, you have to look at the degree of the numerator and the denominator. In this case, both x's have a power of 1. If they are equal, all you need is the coefficients in front of the x's with the highest power. In this case, the coefficient in front of the numerator is 1, so my horizontal asymptote is y is equal to 1 over the coefficient of the denominator is negative 1, which is negative 1. So the leading coefficients of the numerator and the denominator, the ratio of those will give you a horizontal asymptote, which is negative 1. The last example we're going to talk about is this rational function, which can be manipulated and reduced. Notice the numerator of this function. We have x in both terms. In other words, I can take an x out, leaving me with x plus 4. In the denominator, I have x squared plus 3x minus 4. That can be factored into x plus and x minus, and I have 4 and 1 as my factors of 4, and 4 minus 1 gives me 3, which is how you would check it. Now notice something interesting happens here. X plus 4 and x plus 4 cancels. When that happens, a hole exists at that point. In other words, x is equal to negative 4 is going to have a hole in the graph. But this reduces our function to x over x minus 1. And from here, a vertical asymptote is just found by setting the denominator equal to 0. In other words, x equals 1. And a horizontal asymptote is just the ratio of the leading coefficients, because the powers at the top and the highest power of the bottom are equal, which means y is equal to 1. Let's take a look at the graph of this function. We have vertical asymptote at x equals 1. This is x equals 1. This is my vertical asymptote here. Horizontal asymptote at y equals 1, which would look something like this. And the graph that looks like this. Notice this graph gets closer and closer to the vertical and horizontal asymptotes, but it doesn't pass it. So one thing to note is that at x equals negative 4, some value x equals negative 4 is going to have some y value here. There's going to be a hole. And that is just something to note. Because of that cancellation of x plus 4, it creates a hole. As always, thank you very much for joining me for this video. Please make sure to like and subscribe, and I hope to see you next time.